So I'm going to do 3 questions here. All of question 2 will be in the first video. The second video will be made up of these 2. So question 2A from 2017. First off, the setup. We have a particle A, 350 meters from the intersection, moving towards it, so it's going down like that. A particle or a car B, 150 meters from the intersection, moving to the right. And what we need to do is draw a relative velocity diagram. So we need the relative position first. In other words, you want to see how far A is to the right of B and how far A is above B. Now we know that's 350, we know the angle is 60. So that means that the distance, the horizontal distance from the intersection to just below where A is 175. If B is 150 from the intersection, it means that A is 25 east of B. We're also going to get that distance using 350 times the sine of 60. And that will give us this one here. So we tried to redraw the observer at the origin, the observer being B. Remember, we know the observer because we're looking for VAB, and the second one is the observer. So A relative to B, then the observer, is 25 to the east and 175 times root 3 meters to the north of it. Okay. That's an important diagram to start with to get correct. Then what you want to do is get the relative velocity vector, which I've gotten there, simplified it to that. There are the i's, minus 15 minus 9 root 3i, and there are the j's, minus 9j. You also want to get the magnitude or the speed of that vector, as well as the direction. So remember, the magnitude is the square root of that quantity squared plus that quantity squared. And the direction, we take the positive I and j components, put the j's over the i's and get the inverse tan. And that then will give you the acute angle that the line makes with the x-axis. In other words, it'll give us this angle here, theta. Now the first part of the question is how long does it take to get to the shortest distance? So I've got the relative velocity vector going along that path. I've drawn in the shortest distance, which is the perpendicular distance, and I've labelled a few points. So A and B were there. X is the point where the relative velocity vector would cut the y-axis. W is the point where the shortest distance is, and y is vertically below A. Now what we need to do is get that distance from A to W. So it should be, I know this is relatively straightforward, but it's just trigonometry. If you look at the big triangle, AXY, we have the angle there, which is the direction we previously calculated. We have the opposite, and as a result, we should be able to get the hypotenuse. That's a good start. I'd also get the adjacent, and if you subtract 25 from the adjacent, it will give you XB. Now, with XB and theta, you should then be able to get XW, and you subtract XW from XA or AX to give you that distance. And then with that distance and the speed, you can use speed as distance over time to get the time taken for that A to get to the shortest distance it is from B. Okay, hopefully that's fairly straightforward. The second part though is the time taken when they're equidistant from the intersection. In other words, we're looking for the time when S of A is equal to S of B, where S of A is how far A is from the intersection and S of B is how far B is from the intersection. Remember, A is going to the intersection, so A will travel from that point there, we'll say, to that point, and the distance then is S of A. But B is travelling away, so B travels from that point outwards, so S of B is how far it is away. It's from the intersection out to the external dot there. We also know, though, that the relationship between how far it's travelled in a particular time and S of A is related by the given distance. So 350 is equal to S of A plus X. We also know that 150 plus Y equals S of B. So when we do a bit of rearranging here, we find out that S of A, in this case, is equal to 350 minus X, and S of B is equal to 150 plus Y. That's where the second line comes from. Now you've got to remember that the objects are moving at constant velocity, so speed as distance over time will be used. So X will be the speed of A by the time taken for it to go from that distance to that distance. And then likewise, Y is the speed of B even, which is 15 by the time taken to go from there to there. And if they start at the same time, and we want to see how long it takes for them to get so that they're equidistant from each other, or from the intersection even, the times are equal. So sub that in and solve for t, and that's the first one done. Okay, part B. Part B is an apparent wind question. So the velocity of a cyclist is u in the I direction, and then we're told that the velocity of the wind relative to the cyclist appears to come from the direction 3i plus 2j. If it comes from that direction, it goes in the opposite direction, hence the minus. And if we remember, velocity is speed by direction. We have the direction, so we need to multiply it by the speed, which is why I've got minus x by the direction. The second bit of information we're given with this apparent wind question is if the cyclist changes his velocity to u in the j direction, the wind appears to come from the direction minus 3i plus 2j. So from that direction, meaning it's going to the opposite direction, hence the minus. Again, the velocity is speed by distance. We have speed by direction. We have the direction, and the speed in this case is y. And remember, there's no guarantee that y and x are the same. They could be, but they're not. The next step with apparent wind questions is apply our formula. Sub in these values into it. Look, that's for the first pair of values. Sub in these values into the formula. That's the second one. And then you just left the i's equal the i's and the j's equal the j's and solve. Job done. The second part is a straight use of the velocity of the cyclist is equal to the velocity of the wind minus the velocity of the wind relative to the cyclist. That's the velocity of the wind that you use. In the second part, you're given that, and then you just solve for it. That's the end of the first video.